Well, howdy, physics sleuths and inquisitive souls, and welcome to Dynamic Gravity. So, very big day. I've been waiting for this day for a long time, and unfortunately, I am so hugely disappointed. CERN said that they were going to test antimatter, whether it is pulled down by gravity or pushed up or not affected at all, is the goal of this alpha G experiment that's been in the works for, I don't know, better part of a decade now. I've been waiting for it. And the results have came out, like last week they came out, and it is a mess. It is an absolute mess. They're claiming that it completely disproves any theory saying that anti-gravity is real with antimatter. But and from a Einsteinian general relativity sort of perspective, that is a valid statement to make. But when you look at how I propose how gravity is created in the atoms, with the electromagnetic force through dynamic gravity, that statement does not hold true. I was really hoping that this experiment would definitively prove or disprove my theory, but I thought they were going to measure antimatter. Instead, what CERN measured was anti-hydrogen, particularly anti-hydrogen of protium. And I guess let's go ahead and dig into this. So there are three known isotopes of hydrogen, right? You got tritium, which is one proton and two neutrons, the most unstable and radioactive form of hydrogen. You got deuterium, one proton and one neutron. Here's my cursor. And then you got protium, which is just a proton and an electron around it. And that is the one that they made for the antimatter form. They made some anti-protons and then shot them through like a cloud of positrons and then cooled it all. And then placed them in a magnetic trap where they would try and jack up the trap according to their measurements the best they could to keep the molecules as stationary as possible, and then shut everything off and just see, whether they're recording events of antimatter, degenerator or colliding with matter above the trap or below the trap. It sounds good at first, right? But this is really complicated, man. I was really this is something that I just realized probably about, 5 months ago, I'd say, is that measuring a proton on whether it falls in gravity or is repelled or an antiproton is probably the worst test you could do to prove or disprove any theory of gravity. And you might be like, well, why is that? All right, let's break this down. Right? So antimatter, as most of you, I'm sure you know, is basically the exact opposite of regular matter, in terms of charge. So you have an electron and a positron. The electron's a negative charge, the positron's a positive charge. And if they're attracted to each other because they're opposite charges. When they collide, they revert into energy in the form of photons. Yeah. So, yeah. Basically, if they were to measure a positron, which I was hoping they would measure, that would be a definitive test, because a positron is an elementary particle and it is the workhorse of gravity, essentially, as far as attraction goes. So if they were to have, they're creating positrons and they're having this in this trap and they're shooting, anti-protons through it. And the question is asked, well, why didn't you measure whether the positron is affected by gravity or not? If you already have that, why go through the trouble of making an anti-hydrogen when the positron will tell you everything you need to know? I don't know if they did this and they didn't like the results they got, or if they just haven't thought of this yet, or there's some reason, technical reason they haven't done this. I don't know, but it is super annoying. Yeah, here's just more stuff on antimatter. And then there's some other problems going on here. All right. Let me see if I can bring up something of this, right? Let me see if it'll give us a layout, a diagram of how this experiment is set up, how alpha G works. Yeah, okay. So, yeah, why go through the trouble of making anti-hydrogen and testing that when you have the positrons and you can just test that, and then that will give you a definitive answer. I really don't think there's a reason why they didn't do this technologically. I think it's sinister. I think it's something that they saw that doesn't make any sense, and so they either assumed they were messed up somehow, or they want to sit on it as long as possible and see if they can't figure it out first before they release it. I don't know. It's pretty crazy though, because one of the things they did is I forgot why I showed this diagram, because they cooled. They said that when the atom had so much momentum or whatever, they couldn't measure it, or when they were measuring it, they were getting the wrong results. I don't know. They never said, but they said they felt they had to cool the atom as much as possible to get the most accurate result. This is another huge. There's two huge flaws with this experiment. The first one, three huge flaws. First of all, they should just measure the positron. They could do it. They should have just done it. It would have been 100% guaranteed to know what's what at that point. The second problem is that as you cool atoms or anti-atoms, down to absolute zero, where they're getting close, undoubtedly, what the atom forms is called a Bose-Einstein condensate. And it is a totally different state of matter. And it's basically where when it's cooled, the atom loses its properties as an atom. Like you have a proton with like an electron, and they'll just all of a sudden merge into one sort of entity with no real properties. So it's clear. Heat is absolutely the fuel or the energy that drives the atoms holding themselves together. And hence, according to my theory of gravity, dynamic gravity, gravity itself is also driven by heat, ultimately at one level or another. Or according to Einstein, heat wouldn't matter. So I can see why, they're believers in general relativity. So they're saying, hey, we can cool this atom down to as low as we want, and it's not going to change the fact that it's still going to be affected by gravity. And but according to my theory of gravity, atoms actually lose their ability to generate gravity when they are cooled down. And that is hence going to affect their ability on how they are also affected by gravity too. And I don't know the exact, scale or diagram of how everything would come to play, because no one's ever done these experiments, but it's something people should do. I would do if I had money. If I got paid all day long to experiment on stuff, one of the many things I would be doing. So we got one huge flaw right here. They're cooling the atoms down as low as they can, which is undoubtedly going to be near absolute zero, which is, according to my theory of gravity, going to mess things up. So that's flaw number one. Flaw number two. Here's the actual paper they submitted. On nature.com, very reputable, peer-reviewed article. Observation of gravity and motion of antimatter. Yes, this is all by the people at CERN. They go off their abstract, explain everything. In their conclusion, though, they say, and this shows you how funky things are right? If what general relativity is true, the number they should have got was 1g, right? 1g is what they should have got, is how much their anti-hydrogens are affected by gravity. But instead, the number they got was 0.75, plus or minus. So it could even be lower, could be higher, could be lower, could be damn near half. If they didn't do the experiment, very well, and they cool things down and fuck things up, could be totally different numbers here if that actually is a contributing factor. So think about that. That right there tells you the experiment has failed and is flawed. You have to get a 1. You have to get a measurement of all of the atoms are being affected by gravity equally because they're all the same and general relativity doesn't care. And so you would expect this number to be 1. Instead, they got a 75. So they basically had like 100 atoms of anti-hydrogen and this magnetic trap, and then let them fall or go. And what this is saying is that 75 of those 100 atoms went down and were affected by gravity going down. And 25% of them were not affected by gravity and went up. And one part of the reasoning for this is like, well, gases naturally, interact with each other and want to expand out. So if there was no gravity, you would expect it would be, 50-50. And it's like, okay, if you have enough gas pressure where you have like, pressure coming out from that, then yes, that is going to happen. But we're talking about 100 atoms of anti-hydrogen at a time is what they're able to make and throw into this magnetic trap and test. It's not enough to actually have, positive pressure, air pressure of any sort. Interacting with each other. So that right there is real highly suspect. Right. And then let's break into these things. Here is, oh man, really? I guess I have to do this way then. Right. So this is probably the best chart to see what's going on. All right. This is what they measured. Let me see if I can. Can I bring it up a little bit? I think I can. Okay, maybe not. I tried. Sorry, boys. I tried, but full-size image. There we go. Okay. So this is kind of a layout of the experiment, right? And this one is if gravity is repulsive. This is the one that I'm rooting for right here, this line. And so if they had a bias of 1g, which is what we believe gravity is, we measure it 1g everywhere we go, then this is the number they would expect would be like a 0 on the this scale derived PD and values. And if it was no gravity, then it would be this green line right here, right? Well, this is what, my bad, right here. Well, this is what they, if it was normal gravity, it would be this line. And notice how much leeway they had with it. It would be a lot more leeway with these lines too as well. But they didn't feel like calculating that because, once again, they're believing general relativity. They're trying to prove general relativity. They're not trying to disprove it. They're trying to prove it. Remember that. So these are the numbers, right? And as you can see, it is all up and down. Like they want it to be right here. So maybe they're cherry picking their data a little bit to make sure it's pushed up high enough that it's actually on there. But as you can see, as we go down this chart, it definitely is not on this line. I mean, look, as it expands out, towards the 1G bias opens up, it's not there. All right. So now their statement is it is in line with the expectations of general relativity. I guess they're saying, yeah, but it's closer to what we'd expect with GR than with no gravity or anti-gravity. So GR wins. But these are the results, man. Look at this. It's actually closer, believe it or not, right here at half a G to no gravity at all than 1G gravity. At no point does there we go into the anti-gravity, which I'm very disappointed about. But once again, we're going to break into that and go into what's probably going on here, what I think is going on. But just so you know, these numbers, this experiment, this is garbage, man. These results are garbage. This is not conclusive at all. It's all over the place. It's not. It's like an actual different line. And keep in mind, if general relativity is correct, it has to be here. So this tells you right here the experiment is a failure because either it already by their own metric, it pretty much disproves general relativity for what it is. And they can say, well, we want more accuracy by cooling down the atoms even more, but then that's just going to disrupt how my theory of gravity works and play into the benefit of general relativity. So annoying. But these are the results, and I'm not going to lie, these are pretty damning for dynamic gravity, and I wondered, for a while, like, okay, is this right? If this is truly the results, they didn't mess us up somehow. Is my theory, can it exist with this, And yes, it can absolutely. My theory can still be right on gravity. They have to measure positrons, and it has to happen soon. If they can measure an anti-hydrogen, they can definitely measure a positron. And that's the question I want to ask to you is why didn't they measure the positron? Why didn't they start measuring the positron, then the anti-hydrogen or the proton, and then finally mix them together and do the anti-hydrogen and see what happens? I think they did. They just didn't like the results they got. It is what it is. So you might be saying, okay, well, how is it then, if according to your theory of gravity, if you're saying that anti-gravity with antimatter has to be real, how is it then when they're saying that the results that they got are more in line that it's not real than real, even though it's not really a good fit for either, that you're still right? Well, here's what's going on. All right. This is not an opinion of quantum mechanics or classical physics. Okay, this is my opinion. This is how I see an atom being made up. And if this is true, it makes perfect sense and everything is exactly as it should be. If not, then there's some really weird shit going on like quantum mechanics says. All right, but here's what we got. So we got a atom, or my bad, a proton, right? We got a proton. And it's got a little electron, right? Now this proton is not elementary. It's actually made of 3 particles, okay? 2 up quarks and 1 down quark. Okay? I think the down quark is larger. It is larger. And so it's got 2 up quarks and a down quark, right? Now, this down quark, when they collide things into it, it doesn't happen with the up quark, but with the down quark, when they collide things into it, it breaks apart, and one of the things that comes out of it is an electron. Okay? An electron is somehow embedded or a part of a down quark. And now keep in mind, all these quarks are positively charged, right? All of them. except for the down quark. Now, what happened, what I believe, is an electron is smashed into an up quark, right? And yeah, let's do this. Smashed into an up quark, and then the up quark eats the electron because they're negative. They're opposite polarity, so they attract. And when it eats that now becomes a down quark. And so basically, a down quark is an up quark where you have you have an electron. So this is actually probably a much more better way to look at a proton's innards. Is 3 up quarks with 1 up quark that is attached to a electron. And that electron is just giving this up quark enough negative charge imbalance that 2 other up quarks are actually willing to nestle up to it and to become the entity of a proton. Right? This makes perfect sense to me. And when they smash these things together in particle accelerators, this is what the evidence points to of how the atom is made. But for some reason that I don't understand, this is not a viable option according to classical physics or even quantum mechanics. Maybe there's some experiment I'm unaware of that completely disprove this to be impossible, or maybe they just, I don't know, man. They're told it's this way, and no one ever thinks outside the box enough these days. But so here's the problem, right? We've got a proton, which is positive, okay, and the gravitational field of the Earth is also positive because it's a bunch of protons squished together and electrons surrounding it. And this is a constant ball matter. So let's say this is the Earth. It's positive too. So you have 3 positive entities and 1 negative entity. Ultimately, you would expect this proton to be repelled by a celestial body like the Earth and work its way towards space, like through the atmosphere, all the way to space, and just go to space and just do whatever it does there. And we know this happens because when we take measurements in space, there are all sorts of charged particles, high energy, whatever, all up in space. So we know that happens. All this makes perfect sense according to my theory of gravity. But there is a problem here. If we are talking about protium, right, which is, like I said, this electron with, this proton right here, all this is a protein atom, right? So this is where things get complicated. If it was just a proton, you would expect it to be anti-gravity and go into space, right? So if you had an anti-proton, you would expect this to be the opposite. So it would actually overall have more of a gravitational effect than an anti-gravitational effect. And then the positron would be the anti-gravity, and in the regular matter, the electron would be, attracted to. So all in all, we got 3 positive, and these charges don't add up. These are not equivalent. I think they're 1/3, right? So what we got here, we got 3 charged entities and 2 negative charged entities. But the 2 negative charged entities are more powerful than these 3 charged entities. So what ends up happening is, which way does this atom go of protium? I don't know. I honestly don't know. And this is why it's a shitty fucking experiment they did at CERN. And why I can't say definitively that they proved anything. Because you got electron, which is going to be pulling this atom towards it, attached to this, and an electron also embedded into it, which is still being affected. Otherwise, you'd have no chemistry going on in an atom. So obviously, that charge is not completely neutralized when it gets sucked up by the up quark. And which way is it going to go? I honestly don't know. Logic would say, well, all atoms, you would think, on the same category. But here's the difference, right? If we have protium versus, as I explained, deuterium, say, now deuterium is going to have another proton attached to it, but it's not really a proton. It's going to have 3 up quarks. The difference between a proton and a neutron is a proton is 2 up quarks and a down quark. A neutron is 2 down quarks and an up quark. All right? And the way these charges work out, so essentially these is 3 up quarks that have 8 and 2 electrons. Okay? Now, will this protium go this way or that way in a gravitational field? I honestly can't say because it's such a fucking light atom. It could be neutral. It could legitimately be neutral. Legitimately. Not affected by gravity this way or that way. I mean, it is affected by gravity, but it's at a balance point where it's in the middle. Neutral. But once you add this additional neutron, it almost doubles the weight. In fact, I think it does double the weight of hydrogen, from protium to deuterium, just by adding this one neutron. And now you have a lot more, electrons that are pulling on it. So I believe, personally, a deuterium atom will be affected by gravity. Okay, a deuterium atom will be affected by gravity, and essentially will go this way, right towards the planet of the Earth. Not very well, but enough. But a protium atom, because it is missing the half of its mass that's affected by gravity, I think personally it will go away from the Earth and escape into space ultimately, but not very well. It's still going to be affected by gravity on some level because it does have 2 electrons embedded in this protium atom that are going to very much be pulling towards your celestial body that's emitting the gravitational field. So, does this experiment prove or disprove my theory? No, it does not. Does it prove my theory? Not really, no, because I can't even tell you which direction this protium atom is going to go in a gravitational field that's so on the cusp. Now, if it was a deuterium atom, then yes, I think I could confidently say it should be affected by gravity. And if it was an anti-deuterium atom, that means it would be effectively anti-gravity, and it would be pushed up by gravity, not pulled down. Are they going to ever test the deuterium anti-hydrogen? No, because there's no way in hell they could make an anti-neutron and then combine that with an anti-proton and then combine that with a positron. It's too crazy, right? And maybe 100 years from now, maybe, but not right now. But they definitely can make positrons and antiprotons, and instead of mixing those together to form anti-hydrogen, they can just test those separately. Like a positron would be the perfect test for my theory of gravity. That would definitively prove or disprove whether my theory of gravity is correct, is a positron. And that's what I thought originally they were going to be testing was, positrons and anti-protons. But they didn't do that. So I'm hugely disappointed in this. If anything, this is a mark against my theory of gravity because on some level you would expect it, antimatter, to have an anti-gravitational effect. But because it's protium, the most on the cusp atom there is, it's all over the place. But then again, keep in mind their results. They in their results, they got 75% of the atoms went down, and with a 13% error rate. Could easily be like 60%, which is like right in the middle, which, as I said, is on the cusp for a anti hydrogen atom, which is what you kind of expect, what I kind of expect it to do, is to kind of be neutral, almost, not quite, it's not going to be perfectly neutral, but close. I don't know. I'm just so disappointed in this whole experiment. I waited a decade for this, and it answered not a damn thing. And all it's done is make me doubt everything without really the evidence to be convincing one way or the other. Unfortunate day in science. They can't all be great days. But ultimately, does this prove or disprove my theory of gravity? It does neither. It's irrelevant, almost, I would go as far to say. Now, if they do a test on positrons, or they got to do it soon, I hope to God, or they already did it and they don't want to release it, then that one would definitively prove or disprove my theory of gravity. That would be positrons, 100%. Antiprotons, even that's kind of, like I said, iffy, because it's a mixture of positive and negative charges, and which one's overbearing, which one? I think I know, but am I right? I've been wrong before. I'm sure I'll be wrong again. But the positron is an elementary particle. It has to be what it has to be. No ifs, ands, or buts about it. I hope that day will come soon, and we'll know 100% whether dynamic gravity is right or not. In the meantime, I still believe I'm right. I still believe this is how gravity operates. And I have devised an experiment, hopefully to prove this. But I need a vacuum chamber, and it's going to be, I don't know if I can do this, but I need money, man. I need money to prove or disprove this theory. I'm just a poor boy. We'll see. I'm still working on it. I'm still working on a way to try and convert virtual photons into the opposite polarity. I got an experiment I've been running, but the problem is I have to use very strong magnetic fields, and guess what? Magnetic fields absolutely, totally wreck any scale you're trying to measure anything on. So it is a nightmare. I'm trying to... I just got a balance. I'm trying to devise some way that I can measure this on a balance, or it won't be affected by a magnetic field. But man, it is bad. Anyways, I'm going to leave it there, kiddies. Stay tuned for my next episode. I guarantee it's probably going to be the most revolutionary one ever. I'm going to actually break into my revelations on religion, the afterlife, and ghosts from studies on how gravity works and how I'd have to come up with this. It's going to be definitely one you don't want to miss. Yeah, we'll leave it there. Have a good one. Catch you later, kids. Bye.
Like, subscribe, submit.